Right. So in this video, we're going to solve the differential equation 3y prime plus 2x cubed y equals to 0 using a power series centered at the ordinary point x equals to 0. Before watching this video, it's important that you see the previous video so you get an idea of how of all we're going to do in this video. I have left the link to that video in the description of this one. All right, so let's assume a solution of the form y equals to sigma n equals 0 to infinity of c sub n x to the n. And then y, the derivative, which will be y prime equals n equals 1 to sigma n equals 1 to infinity of n c sub n x to the n minus 1. So we need to take as many derivatives as they appear in the equation. Okay, so in this case, so let's substitute the derivatives into the series into the equation. That'll be sigma n equals 1 to infinity of n c sub n x to the n minus 1 plus 2 x cubed sigma n equals 0 to infinity of c sub n x to the n. Let that be equal 0. So let's introduce the 3 and the 2x plus 2x cubed into the corresponding series. Sigma n equals 1 to infinity of 3n c sub n x to the n minus 1 plus sigma n equals 0 to infinity of 2x cubed, well, not x cubed, actually, I'm going to do c sub n x to the n plus 3. All right, and let that be equal to 0. Again, the n plus 3 comes from the fact that we're combining, we're multiplying the two x's. All we do is add the exponents. All right. So now our goal is to combine the series together so we can get the recurrence relation. However, in order to do that, we need to have the same starting index and the same power of x, which is not the case. So we may need to perform some of the shiftings, that is a complete or an incomplete, or potentially expand some of the terms of the series. All right. Well, so well, the strategy here is to write the single series in terms of, or write all series rather in terms of the highest power of x that we see, like in this case, n plus 3. Here we have an n minus 1. Now, if we ask ourselves, how many units is n minus 1 away from n plus 3? Well, they differ by 4 integers, right? That means, well, if I perform, say, a complete shifting in order to get to plus 3, I would need to add 4. I would need to add 4. I would need to add 4 in all the ends in the series. Then I would have to do the opposite in the starting index, which is subtract 4. Although this sounds legitimately, I mean, in accordance with the complete shifting, this is going to take us to negative starting index. That is 3 units into the dark side of the power series, and we do not want to go there. So let's not do the complete shifting yet. So that means for this, we're going to expand n equals 1, 2, and 3, right? And then start at series at 4. Subtracting 4, that's going to take us back to n equals to 0 as a starting index later. So first of all, let's expand the terms of the series. All right. So for n equals to 1, that's going to leave us with 3 times 1, c sub 1, x to the 1 minus 1, plus 3 times 2, c sub 2, x to the 2 minus 1, plus 3 times 3, c sub 3, x to the 3 minus 1. So that's the expansion of the first 3 terms of the first series, 1, 2, and 3. That means we may go ahead and write our series in sigma notation. However, this time starting at n equals to 4 to infinity, 3n c sub n x to the n minus 1 plus sigma n equals 0 to infinity of 2 c sub n x to the n plus 3. That equals to 0. So on the one hand, let me first simplify, clean up the expansion here. So that's going to leave us with 3c1, okay? 3c1, x to the 0, which is simply 1, plus 3 times 2, which is 6, c2, x to the 2 minus 1, which is just x, plus 9 C3 x squared plus, how about we do the complete shifting on the first series? I'm going to subtract 4 to start it at 0. That means I'm going to add 4 in all ends inside of the power series. That's going to fix the n equals to 4 to an n equals to 0 to match with the second series, and n minus 1 plus 4, that's going to give us an n plus 3. So, number 1, I'm going to write simplified. Let me simplify this. That sigma n equals 0 to infinity, or rather rewrite 3 times n plus 4 c sub n plus 4 x to the n plus 3 plus sigma n equals 0 to infinity up to c sub n x to the n plus 3 equals to 0. All right. Well, now we can merge these two series into a single one. However, keep writing the expanded term, 3 c sub 1 plus 6 c sub 2 x plus 9 c sub 3 x squared plus sigma, one single series, n equals 0 to infinity of, open brackets, I'm going to factor the sigma symbol on the left and the x to the n plus 3 on the right. That's 3 n plus 4 c sub n plus 4 plus 2 c sub n, that times x to the n plus 3. And let that be equal to 0. And we're essentially done with the first step of the solution to the differential equation. Now, here's how we're going to equate coefficient. But notice the right-hand side of the differential equation is all 0. So that means the constant 3c1 is equal to the 0 constant. The coefficient of x to the first power 6c sub 2 equals the coefficient of x to the first power on the right, but there's nothing that means it's 0. Also, that means the coefficient of the quadratic term on the left equals the coefficient of the quadratic term on the right, which also happens to be 0. That is 9c3 equals to 0. And for the recurrence relation, we're going to set the argument of the series 3n plus 4 c sub n plus 4 plus 2 c sub n equals to 0. That's because this is going to be the coefficient of x to the n plus 3. And again, the right-hand side is all 0, so that's why everything here is 0. And again, let me simplify this C1, C2, C3, these little equations here. That means C1 equals 0, C2 equals 0, C3 equals to 0. And we're going to solve the recurrence relation over here, this equation. Well, we're going to solve this equation to obtain the recurrence relation by solving for the C that has the largest subscript. In this case, by C sub n, solve for C sub n plus 4. So I'm going to subtract 2 c sub n on both sides of the equation and divide both sides by 3 n times n plus 4. All right, so c sub n plus 4 equals to negative 2 c sub n over 3 times n plus 4. All right, so this recurrence relation is telling us something very important here, that the recurrence relation skips by 4 units. In other words, each coefficient will only depend on 4 indices earlier. Also, so that means also the coefficients will split into 4 independent chains. All right, what are those 4 independent chains? Well, let me set them up for you. So the one for C sub 0, C sub 1, C sub 2, and C sub 3. All right, each C right here, each 4 C's right here are going to generate their own change. So what I'm going to do to generate um, the change, add 4 to every single subscript. That is C4, C8, C12, etc. What about at C1? Add 4, that's C7, C9, C13, and infinitely many. And then for c sub 2 at 4, that's c sub 8, right? No, c sub 6. Actually I need to go back to this. This is supposed to be c sub 5 and 9 and 13. Okay, my bad. And then this is going to be 2 plus 4, that equals c sub 6, c sub 10, and c sub 14, plus infinitely many ones. Lastly, for c sub 3, we're going to have c sub 3 plus 4 equals c sub 7, c sub 11, c sub 15. All right? Okay, so these are the four independent chains of coefficients. However, check this out. Because c sub 1 equals to 0 right here, okay, and according to what we did before, that means c sub 1 equals to 0 along with its entire change. This will be all zeros. Because c sub 2 equals to 0, c sub 2 equals to 0, that means all of the terms, all of the coefficients in its own chain, are gonna be also 0. And lastly, because c3 equals to 0 over here, okay, write this down, rewrite it, c sub 3. C sub 3 equals to 0. This is 0 along with all of the coefficients in the generated chain. So that means all the only coefficients we need to generate to obtain are the ones for c sub 0, c sub 4, c sub 8, and 12, etc. That means the coefficients for n equals 0, n equals 4, n equals 8, and n equals 12. Potentially just the first three. We may not need to do the fourth one. All right, so here we go. Let's generate the coefficient. So for n equals to 0, right? So for n equals 0, according to our recurrence relation, which by the way, let me box it. Uh, C sub 0 plus 4 is 4 equals to negative 2 C sub 0 divided by 3 times 0 plus 4, which is simply 4. We'll just write it as a 3 times 4. All right? And then for n equals to 4, that equals C sub 4 plus 4, that equals, that's going to be C sub 8 equals to negative 2 times C sub 4 over 3 times 4 plus 4, which is 8. But actually, recurrently, using the recurrence, c sub 4 should be written in terms of c sub 0. That is negative 2 over 3 times 8. And by the way, do not reduce the 2 with the 8 over here. That times c sub 4, which is in this case negative 2 over 3 times 4 times c sub 0. And let me simplify this. So that'll be negative times a negative is positive. 2 times 2, that's 2 squared. I know it's 4, but let me write it as a 2 times 2 because we need a pattern for the solution in series form. And then 3 times 3, okay, this is a 3. 3 times 3, which is 9. So wait, no, not 9. Actually, 3 squared. And then 8, let me multiply 8 times 4. So 8 times 4, and that's c sub 0. Then for the next computation, n equals to, what is that? 8. That's going to be with the recurrence relation, c sub 8 plus 4, is that equal to 12? C sub 12 equals to negative 2 c sub 8 divided by, what is that? 3 times 8 plus 4, that equals to 12. And again, this c sub 8 must be written in terms of c sub 0 using the previous computation. So that's going to leave us with 2 over 3 times 12 times 2 cubed over 3 squared times 8 times 4 times c sub 0. Okay? And simplifying this, that should leave us with, okay, 2 to the fourth negative 2 to the, well, actually, it's not, it's supposed to be squared. 2 negative 2 to the third divided by 3 to the third times 12 times 8 times 4. And this is good enough to look for a pattern. All right, so now let's write our solution in series form. But again, we don't need to write the whole thing. All we need to do is simply y equals to c sub 0 plus c sub 4 x to the fourth plus c sub 8 x to the 8th plus c sub 12 x to the 12 plus infinitely many terms. Why am I just writing these terms? Because remember what happened with all of the terms that got canceled, that got zeroed out because of this expansion here? Okay. Well, so in this case, again, just so you can relate to c sub 4, the numerical value we got for c sub 4, that'll be coefficient of x to the fourth. This will be the coefficient of x to the eighth. And this number is going to be, this coefficient is going to be the coefficient of x to the 12. So simply write it into the series. All right. So like green, that'll be y equals c sub 0 plus c sub 4, which is actually it's minus 2 over 3 over 4, with 3 times 4, c sub 0 x to the fourth plus 2 squared over 3 squared times 8 times 4, okay? Uh, c sub 0, x to the 8th. And then what's next? Um, minus 2 to the third over 3 cubed times 12 times 8 times 4. C sub 0, x to the 12, plus, or rather, yeah, plus infinitely many terms. We don't need to write that many terms. This is, again, more than good enough for to see a pattern and write it in sigma notation. Okay, so for this, this is going to be, this is, we're almost there. So y equals to, what is this? C sub n. Let me leave some space for another calculation I would like to do. I'm going to leave some space right here. So that's y equals to c sub 0 sigma n equals 0 to infinity of number 1. Do you see how this time we have an alternating series? So that's going to be negative 1 to the n, right? So that produces the first positive term. And then notice how we have powers of 2 in the numerator, so 2 to the n, and powers of 3 in the denominator, over 3 to the n, right? Also, what else do we have? Uh, before, okay, okay, I know there's a multiplication 12 times 8 times 4, which coincides with the power 12. 8 times 4, which coincides with the power 8. 4, which is coinciding with the 4. Let me do another calculation on the side, especially for the denominator, for the part of the denominator. All right. So hopefully you can see how this case. Let me use pink. Okay. This 12 times 8 times 4. Okay, 12 is the same as saying 4 times 3. 8 is 4 times 2. And 4 is 4 times 1. Right? So that means we can write 4 times 4 times 4. That's equal to 4 cubed. And then times 3 times 2 times 1 times 3 times 2 times 1, right? So I'm going to rewrite this whole term in the here on the following page. The 2 cubed divided by 3 cubed times 4 cubed times 3 times 2 times 1. This would be the n factorial, the same n as the power n of 4, 3, and 2. So in this case, let me just bring a power of a factor which is a power of 4, powers of 4, n powers of 4 times n factorial and see how the exponents of x, the powers of x, are 4 times that same value of n. 3 times 4 equals to 12. 2 times 4 equals to 8. 1 invisible 1 times 4 equals to 4. So that should give us x to the fourth power. And this is our solution in sigma notation. Now, our job is to write this in terms of an elementary function. And this is quite possible because we can call for the exponential function because of the n factorial. Oh, forgot the n here. So we can write everything else as a power n, the 2, the 3, the 4, and the x to the 4. We can write it as a single base and everything raised to the n power. So this is number one, the solution in sigma notation. Let me go the extra mile. So y equals to c sub 0 sigma n equals 0 to infinity of -1 to the n. That's a 2 over 3 times 4, okay, times x to the fourth, and everything raised to the n power, and divide everything by n. All right? So, number one, 2 divided by 4, that's a half. So 1/2 times 1/3, that's 1 over 6. Okay, so this will be, I will rewrite this as a c sub 0 sigma n equals 0 to infinity of -1 to the n of u to the n over n factorial, where u equals the simplified form of this, which is actually, I should have included the negative one as well. So let me go back a couple steps and write this with the negative as well. Okay, negative. All right, it's much better, so we don't have to deal with an alternate series. So that'll be c sub 0 sigma n equals 0 to infinity of u to the n over n factorial, where u equals to that x to the fourth over 6, and then this is simply the exponential function. Y equals to c sub 0 sigma n equals 0 to infinity. Oh no, okay, actually no more sigma. That's simply e to the u, where u equals to x to the fourth over 6, which is c sub 0 e to the x to the 4, x to the fourth divided by 6. Final answer. All right.